So here we have the mold. We have the mandrel, which goes in the center of the mold from the core of the bladder. The mandrel is put in the tool, and the tip is fastened down here, and then a tensioning device is put on the butt end of the mandrel here. So the mandrel is held in tension to center it on the inside of the tool. An O-ring is put around the outside of the tool here that allows us to pull a vacuum and get a really high quality bladder. So once we put the mandrel in the tool, pre-tension it, put the O-ring in it, put the mold releases on, close the mold, then we take it over here to the press. And this is obviously a developmental press that we're just using right now for these pre-production bladder samples. The mold is slid into the press here, and then the press is clamped, and then the entire thing is rotated up vertically. That way there's no tendency for the mandrel will stay centered in the middle of the bladder. Once we do that, we take and we mix the RTV silicone. We tried several different types, and I think we found a couple that worked really well. We take and we mix the silicone, degas it, and then we put it in one of our standard resin injection cylinders. This is what we sell to the aerospace industry for resin transfer molding, typically like epoxy resins. Anyway, there's a piston in here. Pour the resin in here. We take a cap, which screws on here to the top, connect it with an injection line to the injection port on the tool. Then we draw down a vacuum in an entire system and all the way from here into the tool, and then we inject the silicone. It takes about 3 to 5 minutes to inject the silicone. Then the mold is heated and it cures in about a half hour. What we envision for production is actually going to a production manufacturing process for even higher quality silicone bladders. And there's actual production methodologies which are real similar to what's used for making, for example, the nipples for baby bottles. And in those type of applications, your cycle times are about 2 minutes. So from a single cavity mold, we can produce roughly 30. Okay, here we have a completed bladder that we've taken from the other room, and we put a little, this is actually a brand new bladder. We've taken and put a steel sleeve on it with a little, basically sort of a fancy wood screw that screws in the end and seals the little hole on the tip. Then on the butt end, we take and wrap some silicone tape around it, a specified number of inches that basically takes up the space in the cavity between the bladder and the outside of the cavity, and the cavity clamping down on this provides the seal. This is obviously a pre-production design. So what we do prior to the rolling is we take our rolling mandrel, which is very similar to the mandrel which was used to form the bladder, same dimensions basically, a little bit different to account for the shrinkage. We take the rolling mandrel and we put it inside the bladder, like so. Actually, there's such a good air seal, you have to burp it and let the air out. Okay. And we don't use a rolling table here. I don't believe that Swix is using a rolling table either. What we have here is a heated table. It's set at 110 degrees right now. And we've got some neoprene rubber with some silicone rubber on top of that. And it's sort of padded up in the area of the waist and down in the tip area. It helps us roll it easier. If you're skilled enough, you can roll one of these alone. Swix rolls these with only one person. We don't make enough shafts here to get that much practice. This is our first ply right here. I guess you could say it's a tip reinforcement 0. When we mold the part, we use a little Teflon sleeve which covers up the steel sleeve and butts into the end of the tube. So in order to get the right positioning on the start of the graphite layout, I'll lay the Teflon sleeve right there, start the graphite, and then I can move that so get the we'll do here is mark the starting of that first 0 as a reference point. That's our sort of our 0 degree point. We've got a sequence that we use. It's not as much for optimization as just to try and get some consistency. I think Swix has done quite a bit of work on sequencing. This is our first full-length 0, and I will start it at the same azimuth as the first tip 0. I think when Swix does these, they do it more similar to a rolling table kind of operation where you lay the prepreg down, press the mandrel onto it, and then just roll. I've got June helping me here to speed things up a little bit. I'm gonna grab that 45. Now the 45 in the sequence I use, I put it on at 170 degrees. This would actually ready better to push from the other side. It's pretty good. You can see this particular preform has got a little shaped to agree more with the bulge in the waist. Okay. This looks real nice. I think the table's warming up better. Then we've got the outer 0, and the outer 0 has been split into 2 separate pieces to try and reduce the amount of bulging. And I'm going to start it at, you can see from the shape of this ply that it sort of has some of the contouring associated with the shape. Using 2 separate ones seems to reduce the amount of puckering. Bulk of the real 0 degree ply. Obviously, we don't roll these really tight or anything. So, when we're done with the rolling, we pull the bladder out. There's actually a good enough seal here with this outer lubricant that you have to try to let the air suck in. And so we've got the preform with the net-shaped mandrel inside it, using our nomenclature. And you probably stockpile these, obviously, in a production operation. Come over to our mold, put the little Teflon sleeve on. And drop the part in, basically. And you can see there's a real simple barbed fitting. This is really a pre-production fitting right now. Real simple. This would obviously be made more production ready for the final production version. But the tool clamping down on that basically seals, provides the pressure seal. Push it in, and I didn't have the program loaded, so computer.
Do what?
Yeah. And what's happening right now is we've got some sort of idiot lights on here that tell us what's going on, so we don't have to look at the computer screen. These lights sort of correspond to control solenoids inside the control box here. We've got the press clamped, the tool is now heating. In a few seconds, the vacuum inside the cavity will turn on. And then what will happen from here on is when the tool hits 200 degrees, the bladder pressure will turn on. You'll see some water damping, which I'll explain to control the overshoot at the high temperature. It also cools the tool in the cool down phase. So right here we have the computer screen, and this is sort of telling us everything that's going on. What you're hearing, the clicking right there, is the steel heating rods are heating up and slipping on the tool, and the sound is echoing through the press. Right now we're into pulsing, and we can see we're on pulse number 3, pulse number 4. What we have here is right now the tool's at 240 degrees. The cooling went on for a second, you'll notice. What we're doing now is we're doing an intermediate hold at 250 degrees for about 2 minutes. And at the top part of the screen, what we have here is sort of the status of most of the key control aspects of the system here. So the press is clamped, the vacuum is on, the bladder is inflated, the tool is heating. There's no water cooling right now, and these are for the operator, whether or not you can demold or lay out. The tool temperature is 250 degrees, set point's 250, and we're at about 11% power. During we started the cycle at 95 degrees. We're 2 minutes into the cycle. We heated up at 107 degrees a minute, average heat up rate to 250 degrees. The pulsing started at 200, it ended at 233. The total time to the start of this intermediate hold was 1.4 minutes. We got a maximum temperature in the hold of 254 and a minimum of 249. We're 1 minute into this hold. At 2¼ minutes, we'll resume heating to the full cure temperature, which is about a minute from now. For this system, we have the vacuum pump just mounted underneath the press. In a production system, of course, you'd have a vacuum system that would supply the whole gamut of 20 presses or something. And over here, this is a temperature readout that's actually less accurate than the temperature used for controlling it. It's really used for over temperature protection. It's completely separate controller that will cut off the power if we get to an over temperature situation. Right now you can see the bladder's at 250 degrees, the press is at 180 psi. Right now, we're about 10 or 15 seconds away from ending the intermediate hold and proceeding up to the 350 degree final hold. So we've gone out of the intermediate hold, and now we're at full power and heating up to the 350 degrees. And this right here gives your current average heat up rate from the intermediate hold. So this is the average heat up rate that we've accomplished since the end of the hold. And you'll see that keep climbing. It starts off at 0 even though the tooling's heating. And it'll sort of peak out right before we get to the next hold. So we're about 70 degrees a minute. You can hear the press start clicking again, which is those heating elements. Let's see, they're 330 degrees. Now what will happen is when we get about 5 degrees below 350 degrees, we're heating up at almost 100 degrees a minute. To overshoot to a minimum, we actually pump water through the tool to damp the heating. And on this particular one, I think we used about a half or 3/4 of a second of a water pulse, and it was immediately followed by an air purge of the water. And that it controls our temperature pretty well. We were heating up at 90 degrees a minute average. Right as we hit 350 degrees, it went 3 degrees over the set point, and the minimum in the 350 hold was 346. So the screen keeps track of the minimum and the maximum temperatures. For every cycle, we get this entire set of information, which is sort of a summary saved to a file. We also get a data logging that's at about every 4 or 5 seconds of all the key press and control system parameters that's saved to another file. So we have that for each part we make here. So we can look at it afterwards. So right now we're about 1.25 minutes into the 350 degree hold, and I think this particular cure is a 2-minute hold at 350. So when we hit 2 minutes, what will happen is the water cooling will turn on, and we also drop the vacuum at that point. We maintain the bladder pressure, and then we will water cool down to 170 degrees Fahrenheit, at which point we'll drop the bladder pressure and open the press, and the tool will keep cooling down to 130 degrees. The total closed mold time for this whole thing would be about 8.5 minutes for this cure. What we're using here is NCT 301 Newport, and most of the cures we're looking at seem to come in with like a closed mold time of 8 to 10 minutes. And I think we're going to have to look at one of the fast cure variants of either Fiberite 949 or of the fast cure variant of NCT 301 to try and get the cycle times lower. Both companies have fast cure variants of the prepregs that are 2 to 3 times faster in terms of curing rate. So right now we're cooling. We're at 245 degrees. We've averaged 190 degrees a minute cool down rate. And when we hit 170 degrees, the press will open up. And the total closed mold time on this one was a little under 8 minutes. Here's our part. Looks pretty good. You can go ahead and zoom in. You can zoom in on it if you want. What I'll do is mark this one. Usually do 220 -1. And pull that off. For now, take this little guy out. What I'll do is let it cool down a little bit more before I pull the bladder up. It's a little bit easier on the bladder if it's cooler. See, there's almost no flash, and I'll just bring this with us tomorrow. To clean the tool, Swix's tool have a better surface than ours, and they're they're actually able to just blow with air and blow a flash off. Ours weren't treated the same way as theirs, so we actually had to scrape it off. There's a simple sealing step that's used in an anodizing process, which basically makes the tool release far better. That we didn't do on this tool. We were making it apart, we just put the thing back in. Just put it back in. I think we'll be getting O-rings that are more permanent. And then to get the bladder out, all we do is pull it. And this one, you get some pictures of that, and I'll actually just scrape the flash off. I'm going to take it on the plane. I don't want to carry it all the way. Don't want to carry it all the way down there. Almost no flash.
Beautiful.
Okay. I wanted to just summarize a little bit some aspects of the control system. There's a lot of complexity in what the control system can do, but it's inherently simple in its basic elements. It's also very well suited to doing a SCADA type system, which is a distributed control type of system where you have one computer that would run 20 or 40 different presses, so that a supervisor could watch everything that's going on, but the local control would exist for starting the cycle, aborting cycles, or whatever. What we have here is all of the air hookups are on the wall. In a production situation, you might have 2 or 3 different air pressures that you'd be using, so you'd probably run probably two different pressures of air lines to each press, and then you'd also be running a vacuum line to each press. The unit on the wall there is basically just a power supply unit, and what we have in there is just basically some big solid state relays that turn the power on and off. I'll go ahead and open this up. Hope there's enough light in there. Basically what we have right here, and actually the system is operating right now, but we have a little microprocessor which is linked into the computer, and then the computer is controlling it right now. And then we just have a simple relay board here with a relay for each solenoid, and then we're also reading temperatures, so there's input and outputs on these things. But you can see that and then you have a power control unit right there. It's really quite simple for the complexity. An awful lot of the complexity is in the computer program. So, and just give a little bit better feel for what's going on in the tool here. We've got water cooling and heating elements built right into the tool. So these are the copper lines are the water cooling elements. This is a vacuum line right here. We put a vacuum gauge right there close to the tool just so we'd have a duplicate gauge to the gauge that's on the pump down below. And we've got two thermocouples, one that's used for the over temperature protection and one that's used for the computer control. And you can see in the back of the tool the heating elements are actually quite simple. They're basically the same thing that's inside your oven, except you buy them custom and you buy them straight. They're inherently fairly simple and low cost. And then the copper tube is just pushed in to these two grooves right here, and it's actually pounded in so it gets good intimate contact down the length.